So it should hopefully be pretty straightforward to get this to work. So what we're doing when we're using GPU to GPU is, instead of copying from the device to the host and then sending with the host with the send buffer, we just send directly from the GPU. So instead of copying from this location to the send buffer and then sending the send buffer, we just put that in directly, and same for this. I'm just going to, so we're just basically removing this intermediate step. Okay, and I think that that should be that. Okay. So I was just getting an error there because I was defining with G to G both in the command line and in the file. So what's going to happen here? What happened? So I've just recompiled the version that's meant to use GPU to GPU, and what happened? Can anyone tell me what happened? Yep, I forgot to export the variable to tell MPI to watch out for GPU pointers. So it's gone and treated a pointer to something on the GPU as though it was a pointer to host memory, and we've gotten a segmentation fault, which is a good thing. This is what you want, because that tells you straight away that you made a mistake. And if after you've done this enough times, you see the segmentation fault and think, oh, I forgot to export the variable. It's mpitch RDMA enabled CUDA. Mpitch RDMA enabled CUDA. Enabled CUDA equals 1. Okay. Well, it didn't crash. That doesn't necessarily mean that we got the right answer, but so now I'm going to run it and try to generate something that we can draw a picture of. Okay, so that seems to have worked. Because if that wasn't working, then in this picture here, because this has been split into 4 chunks, we would have seen something strange happening here. Maybe the message wasn't getting sent, maybe the information would be teleporting around. It's a very good idea, drawing a picture for this sort of thing where you're dealing with boundary communication. Often if you've got it wrong, you're sending information to the wrong MPI rank, or you're not quite lining things up correctly, a picture will show you very quickly that something's wrong, and usually by using a bit of, deduction, you can figure out what might have gone wrong from looking at the picture. But I'm going to assume that nothing went wrong there. So I'm not going to try to do some timings. It's actually quite difficult to do some timings with this little benchmark to show some interesting results, just because it's a small little benchmark. These are some results I got running a version of this on the old PitStite with the K20X GPUs for a domain with this size here. And this is the time that I got to do 1,000 steps with 1, 2, 4, 8, and 16 nodes, both with the version that used the normal approach, or the approach without G2G, and the approach that used GPU direct communication. And you see for one MPI rank, they have the same time, which is to be expected because there's no communication, so there's no difference. For 2 and 4 and 8 nodes, there's a tiny difference, but it's equivalent to noise. I wouldn't want to say that one is faster than the other. But then at 16 nodes, the G2G part actually gets, the one without G2G communication gets a bit slower, whereas the one with G2G on gets a little bit, managed to continue speeding up. It still wasn't, it wasn't like it was twice as fast. We've kind of stopped, it stopped scaling here, because by the time we get down to 4, 8, or 16 nodes, the amount of work that we've got on each GPU is too small to really occupy the GPU, so we stop getting good scaling there anyway. But at least it didn't start to get slower again. Yeah, so the point is, if you use G2G, it's not necessarily going to hurt your performance, and sometimes it'll actually help. I spent a few years working on the climate and weather code Cosmo for Meteo Swiss, which is now running on GPUs in the PITS cache system that you saw yesterday during the tour. And we used G2G or GPU-aware MPI for that code, and that made a big performance improvement for us. And I was telling some guys earlier that maybe we could have made things a bit more efficient if we'd done all the copying and transferring by hand, but that would have been a very complicated and time-consuming process, and it was much easier for such a large code with so much communication that we had to basically refactor and port just to use G2G communication. I've already talked about this. If you're using, to reiterate, you can use unified memory with MPI, but you have to be, if you're doing that, even if the managed memory is actually located on the host, you've still got to use the GPU-aware MPI implementation, and you've got to use, and you've got to set the environment variable appropriately to tell it to watch out for GPU, for memory that might be on the GPU. So that's the end of that talk about MPI. Does anyone have any questions before we go on? Yes?
Can you also send stuff from the GPU directly to the CPU? So if you do like MPI send, and the sending buffer is on the GPU.
Ah, okay, so you want to send from the CPU on one node to the GPU on another? Yes. Yes, it will handle that situation. To the best of my knowledge, I've seen tests where we've tested this. I haven't tested it myself, but that should be handled, so yeah.
Yeah, I'm interested in the situation when it's
also around. Oh, sorry, the last question was, can you send from GPU memory on one node to a host memory on the other node using this MPI? And the answer was yes. Sorry, your question?
To run more MPI processes on one node and still use GPU.
Okay, so the question there was, if you want to have multiple MPI ranks on one node and have them all share the GPU. And yes, that's possible. I've not done that before, but there is, and I forget the name of it, but there I can look it up later for you, but there is actually a mode, an environment variables that you can set. Sorry? Cray CUDA MPS. You can find the man pages. I'll show you these. The man pages on this Cray system are really rather good. So if we want to find out about something, man MPI, for example, okay, so I've just got the man page for MPI, so this is all about the Cray MPI, and it is a wealth of information about every variable you could want to look for. So if you look for CUDA, you will find, we don't have the Cray. It's not in this. So the environment variable you just mentioned isn't actually in this one.
I think it's a more slow variable because it is independent of MPI. So if you want to have a process multiple processes to use the GPU without MPI, you have to set this. So
okay. Okay, so yeah, so this is something that people have to do, have multiple ranks or threads or processors on a thing. Okay, so that concludes the session about MPI. For the rest, we've got about an hour left, so I would like to talk a little bit about asynchronous work on the GPU. Quit queue. So this is a new session. Oh, what am I doing? I'm getting confused. Okay, so I'd like to talk about concurrency and asynchronous work on the GPU. So in the context of CUDA and GPUs, when I talk about concurrency, concurrency is the ability to perform multiple CUDA operations simultaneously. So what do I mean by an operation? An operation might be executing a CUDA kernel, copying memory from host to device, or copying memory from device to host. That's what I mean by an operation. And also operations on the host CPU. So when you just code, you're running on the CPU. And we might want to run these simultaneously. So you might want to be doing some computation, running some kernels on the GPU at the same time as you're copying data to the GPU in preparation for the next bit of work you're going to do, whilst the host code might be going and looking after some MPI communication for you. And we would like to, if we want to utilize all of the resources available, both the GPU and the CPU, and the network, we would like to be able to start overlapping different tasks and scheduling them. So concurrency, as I said, it lets the CPU and the GPU work at the same time. It also lets you run multiple tasks on the GPU. In case you have kernels which aren't big enough to utilize all the resources on the GPU, you can run multiple kernels at the same time if they are independent, and utilize the resources better that way, and also overlap communication and computation. And there's two main bits of communication and computation overlapping we can do. One is copying data between host and device to get it ready for the next bit of computation you're going to do before you do the computation. And the other is doing, let's say, MPI communication, for example, communication from one node to another. And in an ideal world, we can restructure our algorithms and our codes so that we can always be doing some computation whilst we're doing communication for another part of the computation, so that we're not in a situation where we have to, all the computation has to stop and wait for some communication to happen before it can continue. That's a classic kind of serial bottleneck that you can have in an application. So to recap, we saw this diagram a couple of days ago. What happens when I launch two kernels on the host, and then I run a couple of host functions? What happens by default? Something like this. On the CPU side, on the host side, we have two small functions, I run one after the other, which basically launch the kernels on the GPU. And then the two CPU functions, CPU1, or host, this should be host 1 and host 2, they execute. And then the work on the GPU is run asynchronously or at the same time. It might be run asynchronously. It depends. If there's already a whole bunch of work going on the GPU, we might have to wait quite a long time before these get scheduled to run. But here there was nothing on the GPU, so they were able to start immediately. So you can see that work is done both on CPU and on the GPU. So the CUDA language, yes?
Does it manage dependency when you start two GPU kernels?
Sorry?
Does it manage the dependency? Just say the argument of the first CUDA kernel is X, and the second one is also X. So you have to execute the first one, and then the second one.
Okay, so by default, if you don't give the GPU any scheduling information, it's going to run in what we call the default stream. We're going to learn about that in a moment. And that means that both of these kernels are going to be put one after the other in the default stream and it's guaranteed that they are run in issue order, one after the other. That means that the first kernel will be run before the second one, and I mentioned this yesterday, CUDA makes a guarantee that all memory operations performed by a kernel will have been completed and will be visible to the next kernel that follows it in the stream. So let's say the first one modified X and the second one was reading X. If they're running, two kernels running one after the other in the same stream, it's guaranteed that the second kernel is going to see the changes to X. If you put them in different streams, then all bets are off. So CUDA language and runtime gives us two basic mechanisms that we can use to control asynchronous application running, asynchronous or asynchronous work on the GPU. The first is CUDA streams. So different CUDA streams can concurrently run different kernels at the same time. And a CUDA event is something that we use to synchronize between streams, because once you start saying run these bits of work simultaneously in different streams, you then might have dependencies where, okay, I need to wait for this one and this one to finish before I can do the next step. So you need some way to start synchronizing between streams. So a CUDA stream, we can think of it as a sequence of operations that execute in issue order on the GPU. So remember, I defined an operation earlier to be a CUDA kernel or a memory transfer. So, and if you put operations into a CUDA stream, they're guaranteed to execute in issue order. That is, the order that you say to execute these items in the GPU, the order that you describe them, that's the order that they will run in the GPU. So operations, and the key point here is that operations in different streams, if I create two different CUDA streams and I put some memory copies in one and a compute kernel in another one, they may run at the same time. Now I say may here, they may run concurrently because let's say I put a kernel in this stream and a kernel in this stream, they're only both going to run at the same time if there's enough resources on the GPU for them both to be present. If one of the kernels is really big, if it has many thread blocks and uses all the resources on the GPU, that one kernel is going to run and the other kernel will have to wait until that kernel has started to complete and some resources on the GPU become available. And operations in the same stream, as I said before, they're executed sequentially. And if when you launch, because at the moment we've not been discussing streams, and when we've been launching our kernels, we've not been specifying a stream, so they all go into what we call the default stream, or the zero stream, or the null stream. So there's a default stream that if you don't specify that you want to run in a specific stream, everything just goes in there. And we've been relying on that to make sure that all of our work is nicely synchronized. So if we want to manage streams, the CUDA runtime library provides this thing called a CUDA stream CUDA stream type, and a couple of functions that we can use to create and destroy them. So if you want to create a new CUDA stream, let's say a special CUDA stream to handle all of your copying from host to device memory, you declare it, then you use this to create it, then you can run your work in it, then when you're finished with it, you can do a CUDA stream destroy. And then once we've created our stream, and we want to launch a kernel to run in that stream, we can use it as an additional parameter when we launch the kernel. So remember, we always have to supply a grid dim and a block dim. And there was an optional parameter here for the shared memory size. And there's an additional optional parameter for the stream. If you don't put any parameter in here, it's the same as saying the zero stream, the default null stream. So CUDA stream T underneath is just an integer. It's just a type def of an integer. So here's a basic example. We declare our CUDA stream T, we create it, and then we can launch a kernel to run in that stream. And then once we're finished, we can call CUDA stream destroy. We don't have to use a device synchronize to wait to make sure the kernel has finished running before we destroy the stream. Stream destruction is an asynchronous operation. So if you've already got a whole bunch of work in a stream and you call destroy on that stream, it'll schedule the destruction of that stream to happen after the last bit of work that's been already put in that stream. So you're not going to, you don't have to worry about that. It's actually an asynchronous operation itself. So here's an example of launching 3 kernels, kernel 1, 2, and 3, and we're launching them in 2 different streams. The first kernel goes into stream 1, the second kernel goes into stream 2, and then the third kernel goes back into stream 1. And here's, so here we see the 3 kernels getting launched, and here we see a potential scenario, potentially what might happen. The first kernel will start executing in stream 1, then the second kernel can start executing before the kernel 1 because they're in different streams, but kernel 3 is going to have to wait for kernel 1 to finish executing. Is that clear enough? But I have to emphasize that this isn't guaranteed to happen, because if any one of these kernels is big enough to take all of the GPU's resources, the other ones are just going to have to wait. But this gets managed for you by the CUDA runtime and the hardware. You don't have to worry too much about that. So I've mentioned that kernels are CUDA operations, but we've also got memory transfers, and so copying from host to device. Now, we've looked at the CUDA memcopy function on the first day, and you might remember I said that this is a blocking operation. That is, when you call CUDA memcopy, the function call doesn't return until after the transfer of the copy of information from host to GPU or GPU to host or just from GPU to GPU has been finished. We have an asynchronous version of CUDA memcopy that you can call that will start, or it will schedule a memory copy, and it will schedule it in a stream and then return control to you straight away, so you can keep on doing stuff. So you can imagine, because when you launch a kernel, you get control back straight away. When you do one of these asynchronous mem copies, you get control back straight away, potentially long before these operations actually begin. So you can actually make lots of these little calls to schedule a whole bunch of work on the GPU and then sit back and wait for all of this work to get finished. So it takes an additional parameter, one more parameter than our CUDA memcopy did, and that parameter is the stream that you would like this to occur in. And the host can do other work, but only if we use something called pinned memory. So I touched on this earlier, this page-locked memory that makes the promise to the promise that the operating system is not going to swap any of this memory out to disk halfway through the copy. And we need memory to be in. We need to be in pinned memory for the remote memory access to work properly. So, and copies in the same direction. For example, if let's say I say I want to have 2 asynchronous copies from host to device, they will happen one after the other. They will be scheduled to happen one after the other because we've got basically one devoted stream or one devoted, I don't know what you call it, copy engine, I think it's called, for copying from host to device, and another copy engine for copying from device to host. So so you've got one for copying in one direction and another one for copying in the other direction. So you can be copying from host to device at the same time as you're copying from device to host at full speed, and they won't interfere with one another. So it's not like, if you're copying in one direction, one in the other direction, it'll slow down the overall bandwidth. You'll still get the full bandwidth. There's a devoted copy channel for going in one direction, devoted channel for the other. And if we're on a PIT stiant, the maximum bandwidth you can get is about 11 gigabytes a second in each direction. But on these, on these new Power 8 nodes, which have got NVLink, I've measured over 30 gigabytes a second in each direction. Pinned memory, I mentioned before. I've already mentioned what it is. CUDA provides an API function call that you can use to allocate the memory. It's called CUDA malloc host, It works just like a CUDA malloc and CUDA malloc managed. And it takes a pointer to a pointer and the size in bytes. And we have to use a special freeing function called CUDA free host. You can't use the standard free. You'll get, probably your application will probably crash if you try to do that. So here's an example of where we might want to use, is a common sort of work pattern or a common workflow where we might want to use pinned memory and asynchronous work. And it's a pattern we've seen throughout all of the little demonstrations we've done so far, where you have some data or some information on the host memory, you copy it to the GPU, then you have a kernel that processes that information, and then at the end you copy the answer back. And if this work is what we call like a streaming workload, where you don't need all of the data to be present before you perform the computation, and you don't need the computation to be all the computation to be finished before you copy the information back. I.e., if you could break the information up into chunks and copy the chunks over one at a time and process them one at a time and then copy the information back one at a time, there's opportunities for overlapping communication and computation. And vector addition, this example we did the other day, this is obviously you can break that up into chunks. You can get the first chunk of the two vectors and copy them over, do that part of the addition, then copy the result back whilst you're copying the next couple of chunks over. Dot product you can also chunk up. You could copy chunks over and just take the dot products of the chunks and then copy back the individual results and then collect them together at the end. It's not quite so obvious, but here's a scenario where we're copying from host to device, applying the kernel, and then copying back take roughly the same amount of time. So this definitely isn't the case with our vector addition. Remember, with the vector addition, the amount of time it took to perform the copy was much longer. Like the kernel took, about this much time. So no amount of actually trying to implement a streaming workload is going to help you with vector addition. So what if we were to break this information up into 4 chunks, and we have 3 streams. One stream for copying from host to device, one stream for applying the kernel, and one stream for copying from device back to host. We could copy the first chunk over, and then when that chunk has finished copying, straight away start applying the kernel to it, and when that kernel has finished, start copying back. And when you finish copying the first chunk, immediately start copying the second chunk. And you can just, chain these events together. And you can see that in this situation, if we assume that copies take as much time as the kernel, we can get, theoretically, if everything synchronizes perfectly, a 2 times speed up. This is just one example of how you might want to use overlapping communication. There are lots of other sorts of workflows we can take advantage of it too.
Is there any benefit to have different stream for copying from host to device and from device to host for the same chunk data? Or if you just assign a stream for the first chunk to copy there and then copy back? What is it saying?
Probably fairly similar. I mean, you can only have, so the question was, so I've basically got one stream for all the host to device copies, another stream for the kernels, another stream for all the device to host. What about having one stream per chunk? I think was the question. And I don't know, this one, for me, this is a neater thing because we can only make one copy at a time. In each direction. So we can only make one host to device copy. They don't actually overlap. If you've got multiple copies from host to device in different streams, they don't overlap in my experience. So this way guarantees that they're all scheduled to occur exactly one after the other. But I don't know, it would be worth experimenting with. Maybe when we do the demo, you can have a quick look at that.
Okay, another question. Is there any, or can it be slower to have several asynchronous copying in different streams than have several copying in one stream?
I don't know. I mean, the scheduler is very efficient, so hopefully it shouldn't be much different. So to make all of this work together, we've got the different CUDA streams, but we still need some way to synchronize these operations. That is, we need some way to say, start copying this, and when this copy is finished, then execute the kernel. But don't start executing the kernel until the copy is finished. And likewise with the copy back, you need some way of saying, of actually synchronizing computation between different streams. Because as we've seen, if you just start launching stuff in different streams, they will potentially start launching, they'll potentially run at the same time. And you've got to make sure that you synchronize things. And CUDA provides CUDA events, which are the basic little building block that we use to synchronize streams. So you can use them to synchronize tasks in different streams, as I said before. And you can also use them to query the status of different tasks. So if I launched a kernel or a copy operation a while ago, I can use a CUDA event I can query a CUDA event that I inserted in that stream to find out, has that kernel finished running yet, or has that copy finished running yet? And then I can also, by inserting events in a CUDA stream, and we'll see this, if I insert CUDA events either side of an operation, once that operation has finished, I can then use those CUDA events to calculate how long that operation took to complete. And there's a bunch of different functions. I mean, we don't have to really dig into all the details. We don't have enough time, and it's not very exciting teaching to go into detail about all of these. So I just want you to know that there's a bunch of functions you can use. The CUDA event T is the type that we use for a CUDA event. We can create and destroy events, and then we can do things like record an event. By recording an event, you're basically inserting an event into a stream. You're saying, okay, put this event into this stream. You can synchronize on events. So you can then, if you say CUDA event synchronize on an event that you've put into a stream, that will wait until all of the work in the stream that was put in that stream before you put that event in there, it will wait until that work has finished before returning control to you. And you can also do an event query, where you can ask an event, what is your status? Because you can imagine if I put a whole bunch of our CUDA kernels, one after the other, in a stream, and then I put an event down the end here, I might come back later and say, have all those kernels finished? And the way that I do that is by doing an event query on that event and saying, have you been reached yet? So you can do this. You can just do a CUDA event query. That will return a code that you can then look up. And then CUDA events elapsed time. This is where you might put an event in a stream, then put a kernel here, put another event there, and then if you wait until this event has been reached, you can then, with the first and second event, you can join them together. You can then query what was the time between these two events. And this is what you have to use if you want to really accurately time kernels and memory transfer operations on the GPU. Because as we saw on the first day, if you just try to start and stop a timer in the host code either side of a kernel launch, you end up with you don't actually measure how long the code took to run on the GPU. So it all gets a bit messy, but here's an example of using events to time a kernel execution. So we have some events which we call start and end in a CUDA stream. We create the two events, we create the stream, then we record the event inside the stream. That is, we're putting the event into the stream, then we run our kernel in the stream, and then we put another event in the stream, and then we call CUDA event synchronize. And this says, now we're just going to wait until this event, that is this end event, the one that we inserted after the kernel, we're going to wait until that event has been reached. And then once it's been reached, we can ask for the elapsed time. If you ask for the elapsed time before that event has been reached, you're going to get an error. Because it's going to say, well, the event hasn't been reached. It's not logical. and then you can print out the time it took. It returns the time in milliseconds, so if I want to have a look at the time in seconds, I have to scale it by 1,000. And then at the end, we can call CUDA event destroy and CUDA stream destroy to do this. Here's an example of synchronizing the copy of information from host to device, and then a kernel, and then synchronizing the copy back. So this is I'm not going to go into too much detail here because it's just big and confusing. But the point is we create 3 streams, one for copying from host to device, one for executing a kernel, one for copying the data back. It's a slightly contrived example. And we basically put the first copy in the first stream, then the kernel in the next stream, and the final copy in the last stream. And then we use events to make sure that the kernel doesn't start executing until the first copy has been finished, and so on and so forth. If you want to help getting to sleep tonight, you can actually try to understand what that's doing.
In this example, how have we jumped our copy stream?
Sorry?
In this example, how have we jumped our...
There's no chunking here. This is just a big... Yeah, as I said, it's a slightly contrived example. You might as well put them all in the same CUDA stream and not have... Yep. So this is just an example of how to synchronize things, but you wouldn't, have this in your code. So we have some exercises. These exercises don't actually involve any programming. They just involve looking at some code and running nvprof on it. So I want to, just before, so these 2 examples here, obviously they're pretty messy and hard to understand, and a lot of people actually write CUDA code GPU applications that look like this. You're going to make so many mistakes, and it's going to be messy, and the next poor guy who comes along after you and tries to understand what it was you were doing is going to swear a lot. So I like to wrap these things up in nice little simple types that do a lot of the bookkeeping for me. So this is our timing example before with some little wrappers that I wrote that you're going to see inside the examples. And these look after creating these types and looking after error checking. And they also look after when we finished with them, they use this RAII principle to then clean up the resources behind us. So this is what the copy looks like, and this is what the coordination of the creation and coordination of the streams example looks like. So all of this code here becomes that. And hopefully this becomes a bit easier to understand. I create 2 streams, I allocate some memory, then I copy to the device async in this stream, then I put an event into this stream, then I make the kernel stream, make sure whatever I put into it after now is going to wait or sync on this event, and then I call my kernel in the kernel stream. And this has done all the synchronization under the hood for me and is a bit easier to understand. Okay. So let's have a look at this example code. Okay, we've got half an hour, so I was going to present a little bit about the CUDA cub library. We don't have an awful lot of time left because I want to get all of my stuff finished before lunch. So we've got 2 options. Either I can just kind of walk you through this and we can kind of do it together quickly and then I can show you the cub library, or if you want to, you can take the time to go through this stuff yourself. Who would like to go through this quickly and look at the cub library? Okay, that's a strong majority. So we'll go through this stuff quickly. Let's have a look. Where's the code? So I have to look in the util. Okay, so this copy to device, the first question is what do copy to device and copy to host async do? Let's make this a bit easier to read. Can everybody read that? So they look very similar to the copy to device and copy to host functions above, but they take an additional parameter, which is a CUDA stream. And by default, they put if you don't specify a parameter, they put it into the null stream or the default stream. And they call CUDA memcopy async. So nothing too special there. And malloc pinned host, or malloc pinned host, I think I've just called it pinned now, just allocates some pinned memory for us. It looks just like the malloc host, but now it uses CUDA host alloc instead of malloc to do the allocation. So I've already gone over this. The CUDA event, there's some header files here, CUDA event and CUDA stream. And these are wrappers around the CUDA event type. So when we create a new one, its default constructor calls the CUDA event create and checks that everything worked. And the destructor automatically destroys, looks after cleaning up behind us, so we don't have to explicitly call CUDA event destroy. It gives us access to the underlying event, and it lets us, we can wait on that event. So this will just make the host code, this will wait until the event has finished before returning control, and it gives us a little helper for calculating the time since another event. So for example, I could actually improve this by having a little check in here, querying the event, because this will crash at the moment if this event hasn't actually been reached in the stream. I could add an extra little check in here that would check, we could query the event, and if the event hasn't been reached yet, we could wait on it before getting the time. I would say I wouldn't call these little examples production ready. There's a lot of very careful design that would actually have to go into making one of these really, really nice. This is just an example of how we would start to go about wrapping these types up so that we don't end up shooting ourselves in the foot. And the one for the CUDA stream is similar. It just is a wrapper around the underlying thing with some little helpers and some sugar that make it nicer and easier to use. So the async memcopy1, what does this benchmark test? I don't know, I haven't looked at it for a while. So what does this do? This copies, we should expand these lines. So we allocate some memory on the host, and we allocate some memory on the device. We copy the data to the device asynchronously on a stream, on our CUDA stream here. Then we apply a kernel, and we do the kernel in the default stream by the looks of things. This won't actually, there should be a CUDA device. This should actually be, can you see the bug? Yeah, this should actually wait until the kernel has finished executing before testing. So there's an obvious bug that I just spotted in my code. So I think there's actually a bug in this code because we're not actually using the CUDA stream here for our AXP. And we're not actually synchronizing this stream on anything. So I think there's actually a bug here. But I think this should actually be zero shared memory and then stream dot not the best syntax. Not the best. So what this is doing, and this is basically copying data asynchronously, running a kernel, and then copying some result back, and then it's using some timers to time how long it took. And we can call this, we can test the time now because we've put one event in at the end of the stream after all these operations, and we wait on that event. So because we've waited on that event, we're guaranteed that all the other events in the stream have been finished, so now we can use these events to get the timings. And this will go and measure the bandwidth. And we have two options here. We can either allocate the memory using pinned memory or using normal host memory. And the question was, well, does that make any difference? And the answer is, depends on how big your array of data is. If you've got a big array of data, like megabytes or gigabytes in size, then there's no difference really between pinned memory and host memory. But if the amount of data in your array is very small, a few kilobytes, for example, or a megabyte, it's much faster to use pinned memory because the way the memcopy works under the hood, if you just use memory that's been allocated with malloc that isn't pinned, that memory still has to get copied from the host to the device. It's got to get broken into chunks, copied into pinned memory, a special reserved pinned memory that the CUDA runtime looks after. It gets chunked, put into that pinned memory, and then the remote memory access is used to copy the data over. So for small data sizes, for small arrays, you actually get a noticeable latency, or the latency of that operation, you feel it. But for very large arrays, it uses pipelining, this idea of breaking up this big chunk of data into little chunks, which are copied one after another, and then transferred over in chunks. So this actually, you stop feeling the effect of, you don't feel the latency of this transfer so much. So the answer is, pinned memory helps if you have small amounts of data that you're trying to transfer. And that's good because you don't want to allocate much pinned or page-locked memory, because page-locked memory, if you use page-locked memory everywhere, you're going to run out of memory very quickly. Because page-locked memory, the operating system, you're removing the operating system's ability to take memory that's not being used and put it on the disk. So you are reducing the amount of memory that's available for everyone else on the system. So the second two look at, basically they implement the chunking of information used like the demo I gave on the screen before. You can have a look at those in your own time. If you'd like to, we can run it and actually have a look at it using NVProf, because this is actually quite a nice example of using NVProf to inspect things. Because a key point I should make, and I think that Tibor's going to make later on, is that one of our main aims is to make sure that we get all of this overlapping of communication and computation correct in our application. So we do a lot of work to try and make sure that this happens. But there are lots of subtle little things that can happen that stop things from working asynchronously. And it's very, very difficult to figure out, is my code running asynchronously? Is it all running how I think it is? What's going on? Why is it slow? And using NVProf and the visual profiler are very good tools to help you understand this. So you should always, if you're trying to do this sort of work, every time you make a change, run through NVProf and have a look and try to understand what's going on, and if things aren't working the way you think they are, and the first time you try it, they definitely won't, they won't all overlap very nicely for you. You can use these tools to help you. So I might actually have a go at that. Mem copy 3. So here we use this Newton algorithm we looked at the other day, because it actually does quite a lot of computational work. So the amount of time spent doing the kernel is roughly comparable to the amount of time spent copying. We break. So it takes two arguments. One is the size of the data that we're going to be working with, and the other is the number of chunks that we want to break the data into. And then we have a loop. The loop's over the number of chunks. and we have 3 streams, like we had in the diagram before: a device-to-host stream, a host-to-device copy stream, and a kernel stream. And we copy to device asynchronously, create an event, then make the kernel stream wait on that event. Then we apply the kernel inside the kernel stream, and then we synchronize a copy back to the host on that stream. And the interesting thing is, this for loop, it finishes very, very quickly. If you look in the, when we look in the profile, you'll see all of the body of this for loop finishes on the host very quickly, and then we end up waiting on this last wait for all of the work that we've queued up, all of the little chunks of work that we've queued up on the GPU. We end up having to wait quite a long time for them to finish before we can proceed. So, module. Oh, I'm on my laptop. That won't do. So I'm just going to grab a reservation. So whilst we're waiting for that reservation to become available, so some rough guidelines for concurrency. In an ideal world, you wouldn't want to rely on streams to make sure that your GPU is full of computational work to do. Ideally, you've just got nice big data sets so that when you apply your kernel to them, there's enough work to keep the entire GPU busy and saturate the GPU. You're only really worrying about overlapping kernels on the GPU if you can't find enough parallel work in each kernel to fully utilize the GPU. So there might be, if you have to find yourself playing around with streams a lot, it might be just a sign that your working data sets aren't large enough. Getting full concurrency, getting fully occupied GPU at all the time is difficult. It's a low-level optimization strategy for the last few percent. But this isn't a hard and fast rule. There are lots of workloads where you really do have to pursue this strategy. Where streams really are very useful and they really come into their own and you should use them aggressively is for overlapping communication and computation. So copying from host to device and the other way, and from device to host whilst you're doing computation. These are the much more common and obvious sort of optimization that you can do with streams. So let's have a look if I have got my node. Okay, I've got my node. So, is it mem copy 3? I'm going to do it with 24 and 1 chunk. So let's make that a bit bigger to make a more interesting time to solution. Okay, so that took 0.1 of a second, 100 milliseconds to run with 1 chunk. When I run with 2 chunks, I've got myself about a 25% speed up. 4 chunks. Now remember, in that diagram we had before, I've finely tuned and tweaked this so that the compute takes pretty much the same, roughly the same, as close as I could get to the same amount of time as the transfers. Now remember in our diagram I said in an ideal world, if everything lines up nicely, we would expect to get a 2 times speed up from 4 chunks. I've got about 60% here, so it's not perfect. But if I keep on increasing the number of chunks, that's a bit better. What about 16 chunks? You know, the limit as n tends to infinity is going to be, you're not going to continually keep getting improvement. There's some asymptotic limit to the amount of speed up you can get from this.
I think you're saying that it's a speed up of 1 chunk's worth of computation.
Yes.
So
yep.
It's actually paying exactly into it.
Yes.
Yep.
Yep. So this, So good. So what does it look like when I've done this with 4 chunks? Let's get something that's pretty easy to visualize. We wanted to run nvprof on this, so srun nvprof. Let's put this in a file called async.nvvp. memcopy 3, 26, and let's do it in 8 chunks. So now we're running the profiler on this, and it has finished. So now we can run our, now we can have a look at the result. Can't open display. Oh, did I have profile from start off? Ah. Do I want to save the changes? No, thank you. So let's do that again. So when I was, I don't have the inside this application. I don't have the profiler start and profiler stop set. So I was just running it with profile from start set to off, which means that the profiler never started because it was waiting for me to ask to start it. Ugh. Would I be lucky enough just to cut and paste that? Okay, so we can see that this is where our work has been done, and over here, the first time you call some CUDA API function, it takes a long time, because basically the first time you call a CUDA API function, the CUDA runtime then says, okay, it's my time to start up and get ready. So it will, typically these first few calls will always take a long time, so don't worry, there's nothing wrong with your application. So we broke our data up into 8 chunks. And we see that we have, this is our summary here of our streams. And we've got 3 streams that have been named for some reason known only to the CUDA runtime, numbers 13, 14, and 15. And it looks to me like stream 14 is the one that we're using for host to device copies, because we do a host to device, we do a copy, and then we do some computation, then we do a copy. This will be the copy back to the host. So and if I had, can I show analysis window? Maybe. Yeah. For some reason, I'm finding it difficult to actually see. If you were, when you click on one of these, normally down here in this properties box, you can actually access the information about it. So this would actually tell you that this here was a copy from host to device and what the achieved bandwidth was and how long it took. And if I click on this, this would give me information about the kernel call. But the upshot from this is, after staring at this for a little while, I'm able to convince myself that, yes, indeed, I was able to overlap the memory transfers and the kernels as I intended. Because we can see we've got memory transfers occurring simultaneously at the same time as we have these kernels. So, any questions about that? Yes?
Question about events. How limited a resource are they? How important is it to clean up assiduously your event creation?
I don't think it's that important. You can create a lot of the little guys, yep. And something like HPX, you can imagine what HPX is doing under, this task-based threading system is doing under the hood. It's creating one event for each little feature so that you can time on them and testing them. Save the changes. No. Okay, so we've got about 10 minutes left. So do people want to see the slides about CUB or just take it easy? I'll show those slides quickly. So these aren't slides that I made. They're from some colleagues at Jülich who presented a CUDA training course last year. Now, CUB is one of many libraries out there. It's one particular solution for helping you write GPU kernels. Later on, Tibor's going to present the Thrust library, which is a more high-level library for some basic kind of algorithms and operations you want to do on data. CUB is more low-level in that it gives you a bunch of basic primitive little building blocks for algorithms that then you can then mix and match and combine as you need them inside your kernels. So it provides what they call device-wide primitives. That is, and by primitives we mean things like reductions and scans and sorts. It provides some device-wide ones which you can call from the host to say, use the whole device, the whole GPU with a big grid, with a grid to compute this result. It provides block-wide primitives that you can call from within a kernel that will just do this primitive operation amongst the threads inside a block. So you can do a reduction or a sort or whatever inside the block. And then it also provides warp-level algorithms, so really low-level, just algorithms implemented on a warp level on a group of 32 threads. And so as I said, it's all about collective kernel-level primitives. So by collective, you mean yesterday we talked about synchronization and coordination between threads. So this is a basic set of building blocks that you can use for algorithms that require this sort of synchronization. Because there's a lot of patterns that very commonly come up, like reductions, scans, sorts, histograms, and you often need to use them in all sorts of interesting ways, combine them in different ways to achieve your outcomes. So it's got these collective primitives, but also global primitives, as I said, ones that you can run across the whole device. And if you go to the GTC, that's the GPU Technology Conference, I think they call it. It's run by NVIDIA every year. If you go and search all of their talks, Duane Merrill's the guy who develops this library, and he's got lots of good talks and poster presentations about this that you can look up if you want more information. And the reason why we want to use a library like this is because implementing these basic algorithmic motifs like reductions and scans and sorts in parallel on the GPU is hard. So this is a diagram showing what's going on when or one particular way of implementing a scan operation. I don't know if it's an exclusive or inclusive scan. I can't tell from just looking at that picture. A scan operation on the GPU. And I think it's an important thing to keep in mind is that we could sit down and write, take a few weeks to write a really nice scan operation for the P100 Pascal GPU, and we would use warp intrinsics and shared memory and our understanding about exactly what language features like warp intrinsics were available and exactly how fast shared memory is on that GPU, but it wouldn't work on an older GPU that didn't have warp intrinsics. The CUB library has got implementations for each of these algorithms it provides for not just the most recent GPUs, but for older ones. So it will, at compile time, depending on which architecture you're targeting, it will make the most efficient implementation for that architecture. So I think it was in November last year, changes were pushed to the library for the Pascal P100 GPU. So before they became really widely available, the changes had already been made to the CUB library with optimizations for the P100. Because you don't want to go implementing the optimal version for every single new GPU that comes along. Because next year, when the Volta GPUs come out, which are the next generation GPUs, you'll have to go and rewrite your algorithm. And it's built up of these. Each algorithm, like when you ask for a reduction algorithm, by default, it's built up of some basic lower level primitive operations, which are kind of built up one upon another. And you've got the ability to, if you decide that for some lower level operation, for what you're wanting to do, you want to use a slightly different implementation or a different version of the operation. So for example, if you're doing a reduction across a block, there are multiple different ways it can do the warp level reduction. And you can basically, via a template parameter, reconfigure it to use whichever warp level operation you want, as an example. So I'm going to, and you can tune it. Things like the number of threads in a thread block and the amount of data that's processed per thread, these are all compile time parameters that you put in. So you can tune these. So I think there was a question yesterday that came from the back asking, should I have a thread load multiple data values and process them, or just have one data value per thread? And the answer to that question is, well, that's a good question, and that depends on the architecture and on exactly what your algorithm's doing. And with these, the idea behind CUB is that you can tune this. These just become parameters that you can use to tune, and they made the interface for tuning these very easy. So this is what I was saying before about swapping out. In this case, we're looking at this is what a sorting algorithm called the radix sort, and deep inside it, it needs to use a scan operation, and you can basically mix and match whichever at different levels in the algorithm exactly how you want them to be implemented. So here's an example. We've got an example kernel, and we're going to do a block reduce. So yesterday we were doing a dot product was our reduction that we were doing. So this is what, and we were doing it at a block level. So remember we had each thread block was using shared memory to implement a reduction. Well, this is what you would use if you wanted to do this with CUB. You would use the block reduce type, and you have two template parameters here. The first template parameter is the type that we're going to be doing the reduction on, which is double precision. And the second template parameter is the number of threads. So here you can see where we might want to have that template parameter we were talking about yesterday, showing the number of threads. So we do a little, we create this type, and then this type tells us exactly what sort of shared memory. It provides a type that contains an optimized implementation of data type for the shared memory usage for this here. Because we don't know, it knows how it's going to use shared memory and how much shared memory it needs for 128 threads. So we just ask it to define its own shared memory type. And this here will be a wrapper around some memory. We have the number of items that we want each thread to process. So we're going to have, each thread is going to have 4 values that it's going to contribute to the reduction. And then we call this block reduce type. We pass in the temporary storage, and we ask for its sum function. So we want a sum reduction. There are other types of reductions that it provides for you, and you can tune exactly what type of reduction you want. Min, max, product, etc. And then we would call the kernel something like this. So, and this will look very familiar. Remember, this is what we had on our dot product yesterday. After the result is calculated, thread 0 only one of the threads has to write back the result. And then you can start tuning things. You might say, well, I don't want to make this just work for doubles. I want to make it work for arbitrary types, floats, ints, etc. So you can put a template parameter t in here. And we can also say, well, if I want to load my values from memory, I've got to load my 4 values from memory. CUB also provides nice little algorithms for loading 4 values at a time, or loading values from memory. And it's got different techniques you can use for loading from memory. And depending on which architecture you're on, you might want to use a different technique. And now we're using this trick we use with the union, because we do the load, sync threads, and then the block reduce, and then the reduction. So the shared memory that the load algorithm uses isn't, we don't need that memory when we come down to do the reductions, so we use the union to allocate just enough space to store whichever the largest shared memory requirement is. And then you can add additional parameters like the number of threads in the block and the number of items per thread. So we had 128 threads with 4 items. Now we've made it the parameters that we can specify. But you can see the pattern here. We started out with the simplest implementation. And this is this one here. And this implementation here is a little bit simpler. It is simpler than the dot product we had to write yesterday with the little loop and the shared memory. And then, depending on if that was good enough for your purposes, or if you decided you really wanted to start tuning it and using it elsewhere in your application, you can start to improve on it and start to improve give yourself more options for how you tune the code. And then, as I said before, CUB provides different techniques that you can use to load chunks of data. So if you want each thread to load 4 bits of information, there are different kind of access patterns, different ways you can get threads to work together to do this. And so now we've added this as an additional parameter, exactly how we wanted to do the load. And there are also other different options for how we do the block reduce. Do we just use shared memory? Do we also use warp intrinsics? There are different options. So we may now make these parameters that someone can pass in when they call the kernel. And this uses all sorts of fancy C++ template programming, which you might think looks like a really nice idea or looks like a really bad idea, depending on which school of thought you come from. So you've started from something quite simple, and then as your needs grow, you can build something up. And then this also means that when you go to a different architecture, the next generation GPU, hopefully this library will get updated, and for free you will get to, it'll be much easier for you to adapt your code to that architecture. So this is just an example of the sorts of libraries that are available out there to help you. So we were looking at reductions, but another really common motif is this scan, exclusive scans and inclusive scans. And when you see a lot of the more interesting algorithms that people are implementing on the GPU, things with sparse matrices and graph algorithms, at their heart, they all use scans in one form or another. It's a really common parallel motif a really common kind of algorithmic motif when you're dealing with GPUs to make these things work in parallel. And you don't want to have to implement that yourself unless you really enjoy actually that sort of thing. So libraries like this that actually provide these implementations for you are very useful. And there's, so as I said, you can go and find his more detailed presentations if you're interested in how to use it or how it's implemented. And there's also a nice web page, and the documentation they've got for these is very good. Okay, so that's the end of my talk, and I believe that is lunchtime. Yes, lunchtime 3 minutes ago. So that's basically my material for the course finished. Or we have a question?
Do you know how committed NVIDIA is to keeping this library around? Because it just has one developer.
There's that's a good question. I think there's talk about folding it into thrust. So, yeah, I was just talking to Peter Messmer from NVIDIA the other day. And I think the idea is that they're going to make it part of thrust, because thrust has to be also portable across lots of different devices. And the thrust provides things like sorts and scans at a higher level. And the idea is that they should use this more as the back end in thrust. So I think that it's likely that it's going to, very likely that it's going to stay around, but yeah, I don't know. I'm planning to use it in my application. We got any other questions? Okay, well, thank you very much. I can go get some lunch. So I'm not going to try to do some timings. It's actually quite difficult to do some timings with this little benchmark that shows some interesting results, just because it's a small little benchmark. These are some results I got running a version of this on the old Pitstein with the K20X GPUs for a domain with this size here. And this is the time that I got to do 1,000 steps with 1, 2, 4, 8, and 16 nodes, both with the version that used the normal approach, or the approach without G2G, and the approach that used GPU direct communication. And you see for 1 MPI rank, they have the same time, which is to be expected because there's no communication, so there's no difference. For 2 and 4 and 8 nodes, there's a tiny difference, but it's equivalent to noise. I wouldn't want to say that one is faster than the other. But then at 16 nodes, the G2G part actually gets, the one without G2G communication gets a bit slower, whereas the one with G2G on gets a little bit, managed to continue speeding up. It still wasn't, it wasn't like it was twice as fast. We've kind of stopped, it stopped scaling here, because by the time we get down to 4, 8, or 16 nodes, the amount of work that we've got on each GPU is too small to really occupy the GPU, so we stop getting. So it should hopefully be pretty straightforward to get this to work. So what we're doing when we're using a GPU to GPU is, instead of copying from the device to the host and then sending with the host with the send buffer, we just send directly from the GPU. So instead of copying from this location to the send buffer and then sending the send buffer, we just put that in directly, and same for this. I'm just going to, so just basically removing this intermediate step. Okay, and I think that that should be that. Good scaling there anyway. But at least it didn't start to get slower again. Yeah, so the point is, if you use G2G, it's not necessarily going to hurt your performance, and sometimes it'll actually help. I spent a few years working on the climate and weather code Cosmo for Meteo Swiss, which is now running on GPUs in the PITS cache system that you saw yesterday during the tour, and we used G2G or GPU-aware MPI for that code, and that made a big performance improvement for us. And I was telling some guys earlier that maybe we could have made things a bit more efficient if we'd done all the copying and transferring by hand, but that would have been a very complicated and time-consuming process, and it was much easier for such a large code with so much communication that we had to basically refactor and port just to use G2G communication. I've already talked about this. If you're using, to reiterate, you can use unified memory with MPI, but you have to be, if you're doing that, even if the managed memory is actually located on the host, you've still got to use the GPU-aware MPI implementation, and you've got to use, and you've got to set the environment variable appropriately to tell it to watch out. Okay. Well, it didn't crash. That doesn't necessarily mean that we got the right answer, but so now I'm going to run it and try to generate something that we can draw a picture of. Okay, so that seems to have worked. Because if that wasn't working, then in this picture here, because this has been split into 4 chunks, we would have seen something strange happening here. Maybe the message wasn't getting sent, maybe the information would be teleporting around. It's a very good idea, drawing a picture for this sort of thing where you're dealing with boundary communication. Often if you've got it wrong, you're sending information to the wrong MPI rank, or you're not quite lining things up correctly, a picture will show you very quickly that something's wrong, and usually by using a bit of, deduction, you can figure out what might have gone wrong from looking at the picture. But I'm going to assume that nothing went wrong there. Okay. So I was just getting an error there because I was defining with G to G both in the command line and in the file. So what's going to happen here? What happened? So I've just recompiled the version that's meant to use GPU to GPU, and what happened? Can anyone tell me what happened? Yep, I forgot to export the variable to tell MPI to watch out for GPU pointers. So it's gone and treated a pointer to something on the GPU as though it was a pointer to host memory, and we've gotten a segmentation fault, which is a good thing. This is what you want, because that tells you straight away that you made a mistake. And if after you've done this enough times, you see the segmentation fault and think, oh, I forgot to export the variable. It's mpitch RDMA enabled CUDA. mpitch RDMA enabled CUDA. Enabled CUDA equals 1.